Hello everyone. So today, sorry for the late by the way, because of some technical glitch I couldn't join at one time. But so today, this is the extra week for the course transport phenomena of non-Newtonian fluid. So we will be mostly revisiting the content of the course, and at the same time, what we will be doing is we will be uh, discussing the physical significance of this course in overall uh, analysis, experimentation, simulations, and understanding development of this course, transport phenomena on Newtonian fluids, and the basic fundamental concepts that are uh, so far discussed with you regarding transport phenomena subject, where the momentum transport, thermal transport, and mass transport, everything we have dealt with in detail, right? And I will be revising the main very important key difference between the Newtonian and non-Newtonian fluids. I will be telling you some very important things related to what all the things we have done till last 12 weeks that we were going through, and then I will be telling you about our instructor, Professor Nanda Kishore sir, uh, uh, who has given us insights and his experience on this transport phenomena of non-Newtonian fluids and the basic transport phenomena subject in very lucid manner, and made us uh, and made us very much comfortable with many of the concepts that he has discussed in the course of this particular 12 week, right? So let me just present the slide. So we just present it. Yes. So I am sharing the first screen. Yes. Show my screen anyway, right? So, so if you see this, this one, pin it here. I did pin it. Yes. So pin. Yes. So if you see this one slide, yes. Now it is okay. So this particular week is on transport phenomena of non-Newtonian fluid live session. This is, you can say, week 13, an extra session by B. Saurabh Dubey. And our course instructor, Professor Nanda Kishore sir, he is having immense experience in this particular field. He completed his PhD from Indian Institute of Technology, IIT Kanpur, in 2008, and presently he is acting as a professor in the Department of Chemical Engineering, IIT Guwahati. Hopefully, I am also completing my research here in the same institute, rather in the different department. It's Center for Nanotechnology, and also he was Brunel Research Fellow from December 21 to 2009 to March of 31 2011 at School of Engineering Sciences, University of Southampton, UK. He was a visiting researcher of Department of Chemical Engineering and Processing Engineering, University of Surrey, Guildford, UK, from June 16 to July 16. Uh, and he received Young Scientist Research Award in 2016 from DAE BRNS, IEI Young Engineers Award for the year 2015, a Young Scientist Research Grant from Science and Engineering Research Board of Department of Science and Technology, Government of India, 2013. Right. So sir has provided us very much eased entire difficult concept of the subject in very easy manner, Like the these non-Newtonian fluids are often most of the time we are encountering them in our day-to-day life, and they are the part of many industrial activities. As a raw material they are there, or as a product they are there, right? So they are having lots of daily life applications, and be it personal care product, cosmetics, such as cosmetics, gel, space, food stuffs, such as sandwich spread, ketchup, chocolate, soup, etc. Some of the industrial applications in which are these polymer paints, detergents, and degassing polymer melts and glasses. These non-Newtonian fluids are used in this enhanced oil recovery, non-Newtonian fluidized bed, and water treatments, right? For so this sometimes this production of polymer, alloy, and ceramics via liquid route are also having this fluids there. Pharmaceutical products where these polymer thickening agents are used to enhance their stability for extended shelf life, pulp and the paper industry, etc. Because of the aforementioned overwhelming application of this particular fluids which are there in the daily life and the real systems, it is very important for everybody, be it undergraduate student or postgraduate, like MTech, MS or PG or BE or BTech students or BSc students, to acquire enough academic experience related to the this subject, which is having an amalgamation of everything, this momentum, heat, and the mass transfer, right? Phenomena associated with the non-Newtonian fluids. Why especially the non-Newtonian fluid? Because this particular fluid is the one which is most of the time encountered in the daily life, right? So now I will be having some more points. So these are in this today's class I will be mostly revising, giving you a general brief of this particular course and why this particular course is so important and one of the finest course that is offered only in this particular stream of chemical engineering. Mostly people of different streams can also uh, read or go deeper into this particular subject, but especially the combination of subjects which are offered in this chemical engineering supports the chemical engineering student or researcher of the chemical engineering field to to get them easily trained in this particular zone of the subject, which is transport phenomena, because they are having this mass transfer, they are having this fluid mechanics, they are having this heat transfer. Along with that, they are having very much vast experience about this. If you see chemical reaction engineering, two major parts of the chemical reaction engineering that are those are taught in the bachelor's course, uh, are also somewhere involving the lots of concepts related to fluid mechanics, heat transfer, and the mass transfer. In that, non-isothermal chemical reaction engineering, RTD, catalytic systems, diffusion, adsorption, a catalysis process which is having this rate kinetics associated with that, at the same time the mass transfer or the diffusion of the species from the. So these things are very much important and very much related to the package that is there in the chemical engineering. But obviously the students from the background of civil engineering, mechanical engineering are also very much close, just they are not having this mass transfer and chemical reaction engineering course in their curriculum, but those are they can taste the flavor of those courses through this particular package, which is transport phenomena, right? So so yes, being a chemical engineering, it will be advantageous for you, but at the same time it is very uh, 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 equally important and advantageous with the students of civil engineering and the mechanical engineering, because they are also, or some food sciences students, because they are also having these important heat transfer and the fluid mechanics subjects in their curriculum, but they are going much more deeper into the thermodynamics in terms of steam and pumps, and in those this solid mechanics, right? So those are another part, but those are the one that has to be taken into the. So this different types of mathematical models of the non-Newtonian fluids will be discussed in this particular course, and that has been discussed along the range of first few weeks, and then the momentum transfer, heat transfer, and the mass transport phenomena are discussed along with the corresponding boundary layer flows, which was the part of our last lecture that I had we have taken we have had last week. So yesterday I had class of that, and I'm telling you the particular 1 hour 2 hour class that I have taken yesterday. If you only focus on those things, that whatever I have taught you, and then whatever sums I have suggested you to practice, that 3 lectures will be very helpful and very easy for you, because mostly all the concepts in that we have uh, touched on, right? Through the questions. That is important, because you are developing the intentiveness of about the subject. Okay, so the boundary layer theory flows, and the boundary layer theory, boundary layer development for all the 3: momentum, heat, and thermal, and this mass, uh, we have discussed in detail. So problems, we have discussed many cases of the engineering application where a combination of all these momentum, heat, and the momentum mass, and the momentum heat, mass heat, and the momentum heat and mass together for both homogeneous and the heterogeneous reactions systems where they are occurring together. We have discussed with the examples. We have had glimpse of procedure that are opted, the experimental procedure for the analysis and for the evaluation of various properties of this, this non-Newtonian fluid. And then we have also dealt with this particular very standard model that we study in the fluid mechanics or heat transfer. For example, flow through a pipe. For the case of non-Newtonian fluid, we have discussed flow through the heated pipe. We have discussed, and some problem we have discussed where we are having influence of mass transfer and heat transfer together, or heat transfer and fluid mechanics together, or all the three together. Right? We have seen the parallel plate. We have seen this very very crucial part of this particular course is this is one course which is giving you touch of all the 4 important subjects, and I can say 5 subjects including thermodynamics. So it is giving you the environment or the basics of this fluid mechanics, heat transfer, mass transfer, reaction engineering. Along with that, these all are actually coming from this thermodynamics, right? So this one course is having amalgamation of most of the courses which are being taught in this particular chemical engineering curriculum, and all the real problems that are there are having combination of this particular subject in hand, right? So everything around this subject are coming and actually closely occurring in the daily life applications, right? So coming to the, let me just sort it down. Yes, coming to the next slide. So the course plan was very straight. As you see, the week 1 we have discussed about the basic of non-Newtonian fluids, Newtonian fluids. So non-Newtonian fluids you have discussed. For that, the introduction of the Newtonian fluids were made, and then how these Newtonian fluids are differing from the non-Newtonian fluid, that has been discussed in detail, right? So time independent non-Newtonian fluid, time dependent non-Newtonian fluid, and the viscoelastic non-Newtonian fluid. So different type of non-Newtonian fluid were the part of the first week, mostly the difference between the Newtonian and non-Newtonian, and then what are the different types of non-Newtonian fluid, that was the part of the week 1 that was discussed in detail in these first four lecture of the course, right? The second week was how you are going to calculate the rheological property of any fluid which is unknown to you. For example, any gel in your daily life you are encountering, and you want to measure what is the shear stress to shear strain relation of this particular gel. so as to compute its viscosity. If it is Newtonian, what is its viscosity? And if it is non-Newtonian, what is its apparent viscosity on a given shear rate? So that is the one thing that is very crucial for you to appreciate at this particular point of time, is that uh, most of the liquids around us are non-Newtonian, and then whatever studies so far you have made in your bachelor's and most probably in the masters, those are uh, with the Newtonian fluids. Again, that is an assumption. There is very that is an ideal situation, right? So mostly you are encoding non-Newtonian fluids. So the rheological properties of these non-Newtonian fluids and measurement of those properties are very much crucial for overall understanding of them, because those are the fluid which are being used in the real systems, real application in the industry, food industry, or paints, or any application you take, any industry, they are having this kind of fluid. So this week 2 was on rheology measuring instruments. In that, the week 2 mostly discuss the capillary viscometer. So we have seen how the capillary viscometers are experiments with the capillary viscometers are done, and how we are actually developing our uh, uh, properties, calculating or measuring the property of any unknown fluid. Second, the third week was on rheology measuring instrument only, but this time the instrument is different. So both capillary viscometer and rheology rotational rheometer and then rotational viscometer, they are used for the measurement of the non-Newtonian properties. Okay, yes, that uh, uh, usage, there is some advantages with this capillary viscometer, and there is some associated advantages with this rotational rheometer and rotational viscometer. So with the rotational viscometer, one major advantage is you can calculate or get some information about the normal stress distribution, normal stress differences, which are the main reason, which are non-zero in the case of non-Newtonian fluid, right? So with the non-Newtonian fluid, these are the measurement of non-Newtonian normal stress difference is important, because of those normal stress differences being non-zero, there is different kind of flow structure and some morphologies evolve over the time with the given flow, right? So the next week was the equation of change. So the equation of change, if you see continuum hypothesis and the transport mechanism. So so we saw the continuum hypothesis, where you are actually not dealing with the molecules of each fluids. For example, the length scale or the control volume in which you are working with, there you are assuming the properties to be averaged one, and you are using the average properties for the analysis in that. So MD simulation, if you see molecular dynamic simulation, there we are going molecule by molecule, one molecule or one atom they are working on, and those are discrete methods. But in this one hypothesis, continuum hypothesis, here you are actually relying on the average properties rather going for the statistical properties. So those statistical properties, when you are considering, those are the Lagrangian hypothesis, right? But in the case of continuum hypothesis, you are saying that this particular fluid is having the density rho. Why rho? Any fluid will have different density in different zones depending upon where it is. If a glass of water is there, so glass of water which is exposed to the air will be having some kind of evaporation. So there will be some changes in the temperature at the interface. Even that temperature change will be very small, but there will be, because of that, there will be local gradient of properties. There will be different density. There will be different viscosity. There will be different capacity. Okay, so that is the one thing that you have learned in the lecture number 11. Along with that, you got to know about different transport mechanisms, which are fluid mechanics, which is momentum transport. For that, you are having this mu by rho, which is kinematic viscosity, and then thermal transport mechanism, where you are having this alpha, okay, and then capacity, and then this mass uh, transport mechanism, which is having this TA, diffusivity. Okay, so DABB is for binary systems, and D can also be defined for multi-component system. That is the part of mass transfer course. If you study the first chapter of the mass transfer, any mass transfer course, this is diffusion. Then you got to know about the equation of change for the isothermal. When you are developing that, you derive continuity equation, then the Navier-Stokes equation, and while deriving Navier-Stokes equation, we got this Cauchy's integral equation, Cauchy's momentum equation, right? And this Cauchy's momentum equation is the general one. When you was deriving the Cauchy's momentum equation, it was completely based on the balances. During that derivation, you have nowhere defined that the type of fluid, whether it is Newtonian or non-Newtonian. That's why this Cauchy's equation of motion is valid for both Newtonian fluids and non-Newtonian fluids, right? So those things we have derived. In lecture number 13, equation of change for the non-isothermal systems have been derived. So for the non-isothermal system, equation of change, uh, energy equation, that is, uh, where you have considered influence of everything, the internal energy, the kinetic energy, and the viscous heat dissipation, energy dissipation because of the pressure forces, or any type of additional terms, energy terms, be it because of the magnetic, electric, or some other acoustic, some other kind of phenomena has been can be added up, and final energy balance equation have been derived. That we have many times used for different kind of problems that we have dealt with in upcoming lectures after lecture number 4, right? So this week 5 momentum transfer of non-Newtonian fluid was introduced to you, where this time independent fluids flowing through pipe uh, we have discussed, right? So flow through pipe, this entire lecture was on flow through pipe. Entire week we have discussed with different models, be it this, I mean, this Newtonian, non-Newtonian, starting from this power law, and this model, and then the non-plastic model, and then Hartley, Herschel, Berkeley, fluid flow through the pipe. All these model, for all these model, flow model, you have developed the velocity profile, you have calculated the average velocity, you have calculated the maximum velocity, and then you have also calculated the drag also. Okay, so those things you have developed. CD, track coefficient. You have developed this relation 16 upon RE was for laminar flow, and other equations you have also developed. And meanwhile, you had definition of this Reynolds number for non-Newtonian fluids, Reynolds number definition for the power of fluid, and everything, right? Week 6 was on momentum transfer of non-Newtonian fluids only. In this case, most of the correlations existing in the literature we have discussed. The lecture 18-19 was on transition and the turbulent uh, flow of the generalized non-Newtonian fluids, which were this our power law fluid, the plastic fluid, those things we have discussed, and then we got to know that these many different models through experiments and through simulations people have arrived at, and they have computed the critical properties at the turbulent for the transition and turbulent flow of generalized fluid, right? Flowing through the pipe. So laminar flow of the generalized uterine fluid between the parallel plate are along inclined surface, right? Uh, so after the pipe flow and some basic about the transition turbulent flow for the generalized uterine fluid, we move toward the laminar flow between the parallel plates and also along inclined surface. That is the general cases that can be coming up in front of us in real life. Those things we are slowly and gradually moving towards the river system with different non-Newtonian fluids and their behavior in hand, right? So whatever correlations we have developed in the uh, different week, beginning week for this analyze model, power law model, hum plastic, and Herschel sulfuric fluid. Those are most of the time used while the derivation of parallel plates, inclined surface. As a constitutive relation, we are using those shear stress, shear rate correlations, right? So laminar flow of generalized Newtonian fluid along inclined surface. Also we have done, and then concentric analysis. So this is similar to the one that we have discussed in the rotational revolution kind of thing. So in this one, we have included this generalized non-Newtonian fluids. Okay, so inclined surface is the concentric analysis we have discussed. Now the flow of non-Newtonian fluid through porous media. So the porous media we have discussed in the week 7, where this flow of the non-Newtonian fluid through the packed bed we discussed, and various correlations we have derived, and this part is taught in uh, chemical reaction incident 2 also, and also in the mass transfer. So if those are having this non-Newtonian fluid, then how the packed bed inside the packed bed, how these non-Newtonian fluids would be behaving? Because so far in all everything uh, we have used the Newtonian fluids, right? In every courses of mass transfer that we have done. But here we are having the non-Newtonian fluid through the packed bed. Dispersion in the packed bed also we have discussed for the and how these non-Newtonian effects are playing its role, and what are the problems that these non-Newtonian fluids will be creating. We have discussed. Liquid solid fluidization by power the liquid we have discussed. So this liquid solid fluidization by power law, liquid has been uh, dealt with, and then liquid solid fluidization by power law. Good. Now next week, because liquid solid fluidization by power law we have discussed, we have seen just the packed with dispersion by wet, dispersion in the packed bed, and how this also affects up the liquid solid fluidization by the power law fluids are very important because most of the liquids with the catalyst solid bed, uh, where the bed you are actually fluidizing, and accordingly lots of various applications are there in the real life are involving this employment of these non-Newtonian fluids in the porous media, right? Then the week 8 comes, and from the week 8, this another part, mostly so far we have discussed non-Newtonian fluids and momentum transport. But the only in one lecture before this 8th week inception, which is the lecture number 13, we have came across something non-isothermal or temperature related thing. After week 8, we are mostly having this thermal transport mechanism along with the momentum transport mechanism together, right? So free convection between the two vertical plates we have discussed heat generation we have discussed, temperature distribution in the fluid confined between the coaxial cylinders we have discussed. So those were the very important topics and the very beautiful questions we have solved step by step, so as to make things easy for you. So if you are actually revising all those questions that we have derived, we have discussed, and the questions that are there in this uh, as an assignment given to you as an assignment, weekly assignment of the examples of the lecture, surely you will be going to easily score well in the exams. At the same time, clear your concepts, understand the subject deeply. That is the sole purpose of overall efforts that is made by Professor Nanda Kishore sir and us team, the NPTL, the entire NPTL and SWAM team, and the policies. Because of this, this is provided to you, right? So this the week 9 was on this the thermal phenomena of non-Newtonian fluids. Again, here this temperature distribution for fully developed flow of Newtonian fluid in a tube we have discussed. Heat transfer combined with the chemical reaction as we discussed, and transpiration cooling as we discussed. So till now the lecture number 30 we have touched. So we saw that why transpiration cooling is important and how this transpiration cooling. I have had very separate lecture and a few slides of the transpiration cooling. Please look at the lecture, this week 9 material that I provided to you, and the lecture that is there on the YouTube channel and provided to you. Now the week 10 mass transport phenomena of non-Newtonian fluid. Here the basics of mass transfer is coming. Before this there was no mass, right? Yes, with the chemical reactions that was there somehow, but in this lecture number 29 you can say, but the real introduction of mass transfer comes up in the week 10, right? So mass transfer phenomena of non-Newtonian fluid, uh, uh, lecture number 31 we saw lots of basics of mass transfer, diffusion through the stagnant gas film we have discussed. That was the very important fundamental concept of this transport phenomena in this mass transfer, especially the diffusion, which is and the molecular diffusion, right? Non-isothermal diffusive mass transfer and the forced convection mass transfer we have discussed, right? So, how this, if this diffusivity of between the suppose binary system, so the diffusivity is depending on the temperature. In that case, how the entire diffusive mass transfer or the forced convective mass transfer will change because of the thermal effects on diffusivity that we have discussed, and that was the part of this particular week only. Uh, uh, and then simultaneous heat and mass transfer together, how they will be happening, we will discuss, and then mass transport combined with the chemical reaction we have discussed in detail, right? So, how the chemical reaction happen? So, it is not the chemical reaction engineering, but the basic kinetic equations that we are using, those are the part of kinetics of the chemical reaction. Kinetics part of the chemical reaction, right? So uh, after this, the weak level, where together if you are working with the heat transfer, mass transfer, and the chemical reactions along, if these are there, then there will be momentum transfer system. Then how you are going to solve? So these will be any the transient systems, right? So any transient systems, if you want to solve them, right, then how you are going to do that? Because they are transient in nature, right? So so overall transient analysis is very difficult computationally, and if you want to solve or get some insights of the physical problem in hand, there is one approach that are mostly or sometimes people are doing is quasi-study analysis. So very detailed analysis of the quasi-steady state and how this quasi-steady state is different from the steady state and transition transient we have discussed in the lecture week 11. You can so much deeply we went like deeper than the class about these differences between transient and then steady state and then unsteady state. So transient is more towards the real system. Steady state is very much assumption based, and quasi-steady state is something in between, right? So quasi-steady state analysis of simultaneous heat transfer, mass transfer, and chemical reaction, and then quasi-steady state analysis of heat transfer and mass transfer in different parts. First, second, and third we have discussed, and we reached to the 38th lecture of the course. So this is 12-week course. Usually in many courses you see that so within the frame of 12-week course you will have around 60 lectures, 5 lectures per week. But here, uh, considering the difficulty level of this particular course, only 40 lectures are divided into the span of these 12 lectures. 40 lectures are divided into the span of these 12 weeks, right? Some weeks had 3 lectures or some weeks had 4 lectures depending upon the difficulty level. But the thing is, all the important concepts you are not now having in your hand. The entire package of this transport phenomena is there with you. And if you are research scholar or the or PhD student or the postdoc student or researcher, it can be used or it can be added to the existing setups, experiments, models, or the knowledge that you are doing or imparting to your students or using in your experiments. This can be added on. So this is very handy for you guys. Okay. And then the last week, yesterday, we have discussed on boundary layer fluids. Very important concept. Man, I have very slowly developed the basics of that for you. Introduced you how they are coming up into the picture, how this formation of momentum boundary layer is happening. In similar way, how the formation of transport thermal boundary layer is happening, and I have also explained you that this this transport phenomenon when happening, all the three of these boundary layers are existing together, right? So now just wait. So let me just open it up. So this week 12 that we have discussed, everything on momentum and thermal boundary layer flows, momentum boundary layer thickness calculations for the non-Newtonian fluids. Especially this particular boundary layer is very different from the concepts that of the boundary layer you know till now in any of the course or the basic transport phenomena course that you have done. Here, the fluid is non-Newtonian. The fluid is pseudoplastic, dilated, Bingham plastic, right? So these kind of fluids you have used and you have tried to do the calculations which is more towards the realistic systems that are there in the application, right? And afterwards, in the last lecture, we had this thermal and the concentration boundary layer thickness. So for this thermal and the concentration also you have derived, and for this non-Newtonian fluids you have done. So many problems we have solved with this through the questions for the pseudoplastic system, minimum plastic system, and lots of solutions are as derived for the pseudoplastics, this power systems in the class. So I hope this particular course till starting from week 1 to week 12, if you revisit, you will come to know that lots of very important concepts of fluid mechanics, heat transfer, and mass transfer became very handy in understanding this particular combo course, which is this phenomena. Along with that, with the catch in here, which is non-Newtonian fluid, right? So this is the basic slides that I have used in most of my lectures. For the non-Newtonian fluid, I have used taken it from the Google, which is having telling us this Bingham plastic is something called toothpaste, which we are using daily. So every morning, the first thing that we are using is this non-Newtonian fluid. Then water and the cornstarch, they are dilated. Water is Newtonian fluid or dilated pens. And then this latex pens is there, which is pseudoplastic. Also, this honey is pseudoplastic. So there was this long, big sheet of examples that sir has provided in, I think, first week lectures. What are different fluids and where they? He has also given shear rate between this shear rate to this shear rate, how the things are happening, right? So that we have discussed. So this non-Newtonian fluids, Newtonian fluid, pseudoplastic fluid, dilated fluid, Bingham plastic, uh, everything discussed in detail, and there non-linear behavior, that is the curve between shear stress to shear rate, have been discussed, and we have also had these constitutive models for different type of general models which are available for these non-Newtonian fluids, right? That also we have discussed. Okay, so now if you see uh, the boundary layer theory that we have seen, we discussed that very important concept. There will be fixed some questions coming from this particular slide and this particular topic. So the basic of this particular topic is, let me just expand it a bit. Let me just no, yes. So this particular topic is what is boundary layer. Boundary layer is the reason. Simply just remember, boundary layer is a place where gradients exist. Gradient of what? Gradient of fluid mechanics subject, which is having momentum, which is having velocity. So gradient of V, gradient of heat transfer subject, which is having temperature, that is T, gradient of T, gradient of concentration is gradient of mass transfer subject, which is gradient of concentration, which is C. So gradient of velocity, gradient of temperature, gradient of concentration, that is momentum, thermal and the concentration respectively are the gradients that usually exist in this particular course region, which is this boundary. So have you ever thought this viscous boundary layer or the turbulent boundary layer or the buffer layer exist for what? Momentum boundary layer. Whether they exist for this thermal boundary layer and concentration boundary layer, right? Have you ever thought? So just give a thought about this, right? So, so gradients are velocity, temperature, and concentration exists within the boundary layer. Beyond that, they are towards zero. And that is also uh, reflected through Cauchy's through momentum integral equation, thermal integral equation, and concentration mass integral. Okay, so these were very important in solving many of the questions related to this Bingham plastic fluid and the power law fluids that we have discussed in the last lecture. That was the 12th week of the course. So now you just see how important and handy this particular equations were, that everything we were going to solve was through this particular correlation that again came from the balance of uh, momentum and mass. And whatever equation we have derived, we have reduced that equation. If it is power law based model we have used, we have reduced that equation to the corresponding Newtonian and compared with the classical equations that we have already derived in our UG courses, right? So, what is non-Newtonian fluid? Let's re-revise this because this is the one that is very important. And to tell you about the non-Newtonian fluid, you must again revisit concepts of Newtonian fluid, right? So, this Newtonian fluid behavior in simple shearing experiment conducted at a constant temperature and pressure is given by these important 7 points. So the first point says only stress generated is shear stress. So this is one assumption, and that is the feature of this Newtonian fluid. So there is only shear stress, right? So normal stresses or their differences are zero. So this tau xx minus tau yy will be 0, and tau yy minus tau zz will be 0. Shear stress is linearly proportional to the shear rate passing through collision. Means the graph will be straight. They will not be nonlinear, rather they will be straight, and they will be starting through the origin, right? Then viscosity is independent of shear rate. Right? Viscosity is independent of duration of the shearing. So that is, this is 2 point very important. Neither the shear rate dependent. So it will be having constant slope of shear stress to the shear rate graph, and also viscosity is not depending on the duration of shearing, right? So duration of shearing is actually having uh, this. If the duration of shearing is important, then there is some other category of the fluid which is non-Newtonian fluid. We will be discussing in coming discussion. So let's wait for some time. So viscosities of same Newtonian fluid under different type of uh, deformations are in simple proportion to one. Okay, so very important. And also this stress falls to zero. So, okay, stress falls to zero immediately after shearing is stopped. Okay, so so let's see. So, so now, based on these definitions that we are having, can you just think of what are the properties that non-Newtonian fluid will be differing from the Newtonian fluids? Just think of, just give a thought. Sir has already explained that detail in a very detailed manner. We will be giving 3 to 4 slides on that today because that is very much important. Then you can appreciate all the equations that we have seen, all the discussions that we had in this particular week, right? So this non-Newtonian fluids, if you see, they display one or more deviation from the Newtonian fluid characteristic, whatever characteristic we have seen in the last 7 characteristic. And the rheogram, which is shear stress versus shear rate curve of the non-Newtonian fluid, uh, is non-linear. It is not straight line, and it is not passing through the ocean. So, so this uh, then for the non-Newtonian fluid, you defined the viscosity. It is not the fixed viscosity for all the shear rate. Rather, the viscosity is shear rate dependent, and the apparent viscosity you rather define, which is local shear stress divided by its shear rate, right? and it is not constant at a given temperature and pressure, and it depends then on flow conditions such as flow geometry, shear rate, etc. So, very important and very good source of this differences between the Newtonian and non-Newtonian fluid I found on PDA, and I have used and I have acknowledged here. You can also visit this particular link. There they say that the difference between the Newtonian and non-Newtonian is, if you see, Newtonian fluids are fluid that follow Newton's law of viscosity, which is mu du by dy, right? Is shear stress. Now, this law indicates that the shear stress of a fluid is proportional to the rate of deformation, with the constant of proportionality being viscosity of the fluid. This means that the viscosity of the Newtonian fluid remains constant regardless of the magnitude of the applied stress or the rate of deformation. Water, glycerol, alcohol, and the mineral oil are a few examples of the Newtonian fluids. Now, Newtonian fluid have the ability to flow freely when subjected to the applied stress, right? This is because the viscosity of the Newtonian fluid does not change with the magnitude of the applied stress. Hence, these fluids can be easily pumped or transported through pipes and channels without significant changes in their flows properties, right? They also exhibit laminar flow behavior at low flow rates and high viscosities. Laminar flow occur when a fluid flow is in layers, with each layer moving in a parallel direction to the axis. So this is one. So they also exhibit laminar flow behavior at low flow rates with high viscosity. Laminar flow occurs when the flow is in the layer. So it is laminar kind of condition. Okay, streamlines are in the layer. So you can easily pump this and you can easily transport it. But in the real systems, you see, mostly you are dealing with non-Newtonian fluids, they are difficult to do. So the pumping is required in the real systems, in the industries, in various operations or whichever is there. So it is very difficult for you to actually uh, do this. So they have classified them in this particular differences. You see, for the Newtonian, they are saying the Newton's fluid, they are following Newton's law. Newton's fluid are fluids that obey Newton's law of constant viscosity. Here, non-Newtonian fluids are fluids that do not have constant viscosity. Viscosity remains constant regardless of their magnitude, regardless of the magnitude of the applied stress or the rate of deformation. And here, the viscosity can vary depending on the magnitude of the applied stress. Okay, so exhibit a linear relationship between the shear stress and the rate of deformation, and here it exhibits a non-linear relationship between the shear rate and the shear stress and the shear. Water, glycerol, alcohol, some mineral oils are a few examples of this Newtonian fluids. So you can consider water, alcohol, and glycerol to be Newtonian fluid. Emulsion, suspension, and the gels are few examples of this. So you see this 15 slide is important. You see this Newtonian fluid also have some limitation. These fluids may not exhibit the flow property of the real fluid, world fluid such as blood. So for that you need a non-Newtonian fluid definitions. So the non-Newtonian fluids are fluid that do not follow Newton's law of viscosity, and depending on the magnitude of applied stress, the viscosity of the non-Newtonian fluid can vary. For example, emulsions, suspensions, gels are example of non-Newtonian fluid. So non-Newtonian fluids exhibit shear thickening behavior or shear thinning behavior. Shear thickening behavior occurs when the viscosity of the fluid increases with the magnitude of the applied stress, while shear thinning behavior occurs when the viscosity of the fluid decreases with the magnitude of the applied shear stress. These liquids also show complex flow patterns such as vortex formation, shear banding, and flow instabilities. These flow patterns can significantly impact the transport and the mixing properties of non-Newtonian fluid, right? So let me just make it a point, guys. Then it will become easy for you to actually appreciate this. Okay, so let's okay. They also exhibit time-dependent behavior such as viscoelasticity. This behavior is commonly observed with the polymer solution and gels. So these were important things. So in this one, for the Newtonian, you see this mu apparent is what? Shear stress divided by shear rate, and uh, this has to be corrected. So mu apparent is nothing but mu, and we can correct it like it's what. So I can't write. Let me just fix my pen tablet. So okay, now I can write. So this mu apparent is equals to mu equals to what? Tau divided by for Newtonian. Okay, equal to, and the for non-Newtonian, this is not true. Rather, this mu apparent is a function of what? Right. So now you see this. Last slide about the definitions are the differences between the Newtonian and the non-Newtonian fluid is if you see again the main things are this definition itself is Newtonian fluids are fluid that obey Newton's law of constant viscosity, where the non-Newtonian fluids they do not. Viscosity is what? In a Newtonian fluid, the viscosity remains constant regardless of the magnitude of the applied shear stress or the rate of the deformation, while the viscosity of the non-fluid can vary depending on the magnitude of the applied stress. Flow behavior is what? So what will be happening to the flow behavior? Newtonian fluid exhibit a linear relationship between the shear stress and the rate of the deformation, which is u by du. While the non-Newtonian fluid exhibit a non-linear relationship like we have had between the shear stress and shear rate. So this is the non-Newtonian relationship that I am talking about. Is this one? Where is that slide? Yeah, this one. You see this non-linear graph, for pseudoplastic type. It is not possible to hold okay. And examples are for non-Newtonian are emulsion, suspension, and gels. And for the Newtonian, you are having this water, glycerol, alcohol, and mineral oil, right? So, conclusion is fluids are liquid gases or other materials that continually deform under applied shear stress or external force. Fluid can be classified as a Newtonian fluid, a non-Newtonian fluid, and then the Newton's law, how they are actually following that or not. So, so now you are having enough definition and differences of that. We have seen what all the things we have touched on. So far now, what I will be telling you, I will be opening each of the the, the slides from the beginning, first week to the last week, and what all the questions we have solved. I will be quickly sailing you through from the slides that we have discussed in the span of last 12 weeks. Okay, so that will be helping you in order to actually get revision of the things. So next 50 minutes around, we will be actually giving around 10 minutes or 5 minutes each to the different questions that we have solved. And while that, I will be telling you what are the things you have to take care and what are the things are important in terms of final examinations and the final assignment that you are going to face. And how you should approach this particular subject to actually get maximum out of the tasks that we are performing. Okay, so let's wait. I will be just opening. Okay, so or assignment. So we let's present it. Where is this? So this is the weak one, right? I will just present and close it. So this was the week one of this particular course, right? Very quickly, I will be going through the slides. So, so in this particular week, the main discussion was on the basic differences between the Newtonian and non-Newtonian fluids and the models that are there. So the first question we have solved around this shear stress versus shear rate curve for the Newtonian fluid. And we know that for the Newtonian fluid strict parts, the original source C was correct. So that's what we have discussed here in this particular graph you see. And then units of viscosity of Newtonian fluid we have seen it is Pascal second. I have also did all the steps for you to actually understand this. So you can just go through this particular slide and get information about it. The next question, so this was the detailed one. So the next question was critical Reynolds number for transition from the laminar to turbulent. For the laminar, we know that it is 1000. But this particular discussion again came in our 7th or 8th lecture of the week. Let me just tell you which was it. Which was this one, the 18 and 19, 6th week of the course, where this transition and the turbulent flow of the generalized Newtonian fluid we were discussing. There we just revisited, revised it, right? So for the pipe flow, where the v velocity, fluid with the density rho and viscosity mu is flowing with the velocity v. Okay, the laminar to transient to turbulent changes were happening, right? So So the critical Reynolds number for different systems we have seen, and the critical Reynolds number is what? It is fixed for this for the transition from the laminar to the turbulent flow in the Newtonian fluid inside the pipe flow, that is 2300. So through the interpretation, you got to know that if the Reynolds number is less than 2000, so you are saying that it is laminar around 2300, which is less than 2300, you can say, and if it is more than 4000, then the flow is turbulent, okay, chaotic, and mixed. In between this is the transition zone, right? And then the question on the friction factor F for a laminar flow of a Newtonian fluid flowing through a pipe we have solved. And we have seen that this particular friction factor F for the laminar flow of this non-Newtonian fluid through the pipe uh, is 16 upon RE, very which comes which is used in this Darcy-Weisman friction factor, we call it, and this is used in the Darcy's equation, which is delta P by L equals to 4F V square upon 2GD, right? And also this FD, if you want to say Darcy's one, it is 4 times of F fanning. So F fanning is 16 by 8, right? So this is the detail about the square built with, right? And moving towards the next question was on the Fourier law of heat conduction. Very important, very classical equation of the heat. Also the first equation that you study when you are doing the inception of this particular course. So I think first 11 lecture we will be revising in detail. The last lecture I have done in detail. I will be revisiting. So the last 2 or 3 lectures, it's just the recent. So that is, you can revisit or re-watch those lectures. Around this 12 lectures or 13 lectures, that is 26 hours each. It will be giving. So entire package now you are having the 41 lectures from the third, and then this 26 hour of the practice package through this problem solving sessions is given to you to master this particular force transport phenomenon. Right? So this Q equals to minus K dt by dy is the Fourier law of heat conduction. Okay. So here you see this details are given. The next question was this thermal conductivity of the material and how the unit of this derived from. Randall number, these non-dimensionless numbers are very important in terms of actually feeling the subject. So this Randall number for the Newtonian fluid is defined in a way that the momentum diffusivity, the thermal diffusivity, which is mu by alpha, which is mu by rho, mu by k upon rho Cp, this will be mu Cp mu by k. So if mu by alpha, which is C, is momentum diffusivity to the thermal diffusivity. Based on that, if the Prandtl number is greater than 1, if the Prandtl number is less than 1, or equal to 1, based on that you can actually predict the thickness of the thermal and the momentum boundary layer that we have discussed in the last lecture. So you can relate that, right? So there you have derived it. Okay, so let's move ahead. The momentum thermal and the mass diffusivity, what is the unit of this? So we can actually solve for that. It is meter square per second. Right. So next was this schematic number for a Newtonian fluid and how it is defined. So for this one, the momentum diffusivity to the mass diffusivity. This momentum diffusivity is still in the numerator. Just the denominator changed from the thermal diffusivity for this Prandtl number to the mass diffusivity for this schematic number. Right. So this is DAB, right? So this is diffusivity. So we like this. Just keep like this. Please correct it. Understood, but I have written somewhere. But which is the one correction that can be done. So, so, so based on that, if you see this one, the Prandtl number, if Prandtl number is less than 1, greater than 1, equal to 1. So we had some examples. For example, Prandtl number less than 1 means what? The liquid metals. For that, less than 1 means what? This momentum diffusivity is less than thermal diffusivity. Means thermal boundary layer is bigger. Yes, momentum diffusivity dominates for the greater than 1 case. So this is the one part that we have discussed in the last week also, which is the week 12, in terms of thickness of the momentum boundary layer, thermal boundary layer, and the mass or concentration. Okay, and if it is one, which is for the air, water, and the moderate temperature, momentum and the mass diffusion, in that case, thickness of the boundary layers will also be same. And that this is for the schematic number. The bottom one, if you see, this schematic number, if it is less than mass will be diffusing very fast, so the concentration will be very thicker than the momentum boundary layer, and the schematic number is greater than 1, then momentum diffuses faster than the mass, which is the case for the oil and gases are having less than 1. That will equal better. That was the example for the oils. She's also having oils. Oils are having greater than 1 both will be the schematic. And then the schematic one is similar to the one which was independent and fixed law will define. These are the basic equations. So for the temperature we derived, the original law viscosity you know, which is what the momentum and where the concentration is fixed. Okay, so this Newton's law of viscosity, which is mu by dy. This is fixed law. This here it is for use. Q equals to this like this J minus DAB. So this is the one that we are talking about. Now you have had this second law of fix, which is important, which is different than the usual one. Here you are having non-steady state diffusion. It describes how concentrations change with time. The diffusion applies when the concentration varies in both time and space. The shearing viscosity of the liquid is this one. What is the viscosity if it undergoes unidirectional domination? So this particular correlations you have to use, and you will get that for the Newtonian fluid, it depends on the kind of elongation. Viscosity is proportional to that. The first slide, I think, of today's class, I have had this. That yes. This one. Viscosities of the same Newtonian fluid under different type of deformation are in simple proportion to 1 over. So mu e by mu equals to 3 is, so in that the proportion you can actually use the division. So first division we have used for the question, right? Now, if you see this question number 12, which is very simple, and if you see this one, let me just correct it. Very basic equation, the same equation that we have discussed. Using here for the Newtonian fluid, it is exactly very easy problem. The definition, if you have, this is for this power law model, and for the case of time independent non-Newtonian fluid, it uses to Newtonian fluid. Okay, when n equals to 1, this power law model, n equals to 1, it is Newtonian fluid, value proportional. And then this is a model which is reduced to power law. Under what condition? Cross viscosity model. This cross viscosity model mu minus mu infinite divided by mu naught 1 infinite equals to 1 plus k gamma dot by x is upon n. And this one under the limit of this particular option, which is mu is very small than mu naught, or mu is very larger than mu infinite, which is reduced to the right. So how this happens? This particular slide is in review. So this is the part of the lecture. So from there I have taken this. Then this is the Alice model is question. Okay, so Alice model, what it says is this one which is in front of you. The in this one, the what is this tau half indicates? It indicates the shear stress value at which apparent viscosity drops to half of the unit. Right. Ah, this is another one for the Lice model. This question, this power law is one. In that case, the m is given by this. So these all question you practice. Please practice. It will help you in actually tackling. This is some problem based on the circle model of fluid. Based on that, you solve some questions. Right. This is the approach that you have to follow. Again, some problem on the calculation of these matrices related to algebraic model and Paula models. Right. Then there is this calculation of the Bohr number, and if you remember, we have seen this for a time dependent non-Newtonian fluid, the hysteresis form in shear stress versus shear rate for this function of what? Function of duration of the shearing, rate of the shear increase or decrease of the shear rate, and kinematicity of the rate. Of the shear rate. So these are that is important. Okay, and then this is the main details about the same. This was for the thresholdic. About the Reguera number is the relaxation time to the deformation or absorption time, right? Observation time. So, if this Deborah number between the relaxation time and the deformation time. So how this is derived or defined? Let's discuss about this. The Deborah number is a relaxation time to the observation time. So relaxation time is time a material takes to relax stress after deformation. And observation time is characteristic time scale of the process or flow. Okay, so physical meaning is describes how solid like a material behave during the process. For example, if the water number is very high, means its relaxation time is very high, or the deformation time is or observation time is very okay. Means it is material behave more like solid. It will take very large time to relax. No, material behaves more like fluid. So all the fluids are low Deborah number. So, right? So Alice model related question is again here. The similar question again. Half of the zero zero is possible zero that is there. So this was the first lecture, right? The next one, save it. The next one is week two. Again, we started with the basic uh, classifications of the same. Okay, then this how this capillary viscometer, Newtonian, Newtonian time independent and time dependent are discussed. We have seen and but how this main equation, which is the balance equation, which is used valid for both Newtonian and non-Newtonian, and before this, while deriving this, it was just the balance. We have not introduced any of the assumptions on the property of the fluid or the type of the fluid that we are dealing with. Okay, so the next slide says about this laminar. This is valid for laminar. Any incompressible fluid it is valid, right? Be it Newtonian or be it non-Newtonian. So those things we have discussed. We have seen how the volumetric flow rates are calculated, and finally leading to this particular here. The two shear stress, nominal or the apparent shear stress at wall for the generalized Newtonian fluid. We have Newtonian fluids, which is unlike Newtonian fluids we have discussed. So now, for low to medium consistency fluid, a constant pressure viscometer is suitable because low to medium consistency because the fluid flow radially under applied pressure. The shear rate can be derived from the measured flow rate and flow remains laminar and stable in with sweeps. What are the some problems or difficulties with non-Newtonian fluid because of which their rheological measurements are difficult? So they are nonlinear
there is a dispersive, there is dissipative effects, and then time dependent nature, right? So all are these are different. So rheological measurement, these questions. So this true shear stress calculation, this is A to average by D for the fluids we have used. This is the fluid, and there will be some independent correction that is the part of another one. So, and now the nominal of the shear stress is asked. You see that for the Newtonian fluids, this one is the same, and for the power law if nominal apparent discharge is the same. For the true shear stress, if see, it is modified like this. So that 32 will be modified by this factor, which is 3 n dash plus 1 by 1 n dash. Last one was there. So it will be apparent will increase shear rate. Okay. So for n.5, this shear rate increased for a given shear stress. For a given velocity rate, shear rate increased for given velocity md is same, then it is increased. There will be more shear rate, more shear rate. Yeah. I that fluid must be what? N is less than 0.5. If n is less than 0.5, what kind of fluid you are dealing with? If n is less than 0.5, then what kind of fluid you are dealing with? Are you getting my point? So, the power law model you see, you will be dissipating, right? So, we have done that. Very easy questions we have solved many times. So, in this one, all shear stress is calculated. So, similar questions you will be getting in your final exams, right? So, the thing is, revise these all questions. So read this question again and then see whether you are able to collect the information that we have discussed so far in the course through questions, through class examples, or through oral presentations that were there. That is the main task of the course. So you please read this question or observe this. Right? Meanwhile, I will be joining.
Okay, so I hope you solved it because we have already discussed it sometime, but very easy question. Just you have to play or observe the words, read the question very carefully because sometimes, most of the time, we miss out something by reading the question and then we have to pay marks or we have to pay uh, the cost for that. We end up doing the incorrect solution, right? So this is the one. For any fluid, Newtonian or non-Newtonian, flowing through an infinitely long cylinder, when the length is very higher, length by diameter is greater than 150, under fully developed laminar flow condition, the wall shear stress is given by this. What is the source of error in the capillary viscometer? The end effects, wall shear effects, kinetic energy loss, and the variable head imbalance, viscous heating and departure from the laminar flow condition. These are correct. So these all are correct. So this is so these are the details of the same question that we have seen in the last slide. Okay, so let's revise it, reread it and revise it because it here itself you just complete this. Okay, so end effects and wall sleep effects are there, and there is this kinetic losses, and there is this variable head, then this viscous heating, and because of that there is departure from this laminar flow condition. Okay, so that is the one. So what will happen because of the entry effect in the case of capillary viscometer? The pressure drop will decrease at the entry point of the capillary. It is true or false? So we have discussed this in detail. True or false, and the detailed explanation is below. Please go through this. The thing is, I am just pointing out what all question we have gone with. We have solved. So this was the reduced viscosity. Will be also coming up at the walls. Okay. So then, because of the sleeve effect in the case of the capillary viscometer, the shear rate decreases compared to the case of the low sleeve. So this is sleeve, more sleeve, low sleeve, and then all the conditions we have seen. So these were some very important discussions that we have made. This is the one about which we have solved one question. This is coming in the two shear stress formula, 3m dash plus 1 by 2m dash. Okay, so please look at this and release it. This is the standard formula which is used. Wall shear stress, right? So V2 is done. Let's save. Still 10 to 20 minutes are there, so I will be revising the most difficult lecture, which was this non-isothermal week 4 lecture number third of lecture of the week 4. I will be again taking you to that because next 20 minutes we will revise because that is a bit difficult, and that is that will help you to get through lots of other problems that we have discussed in the present the weeks which came to that. Right? So let us just take that particular slide. It is week 4, last slide, I think. Not actually. Okay, so So this is transport phenomena of non-Newtonian fluid in that equation of change for non-isothermal system. So in this one, this is around 26 slides, and we will be very carefully observing everything because this slide is very important. This topic was a bit difficult in terms of calculation because here some thermodynamics also came into the picture, but this is complete basics, and all the terms are coming up because of the which is leading to the thermal effects in the system, right? So before this, you had this derivation of continuity equation, Navier-Stokes equation, and before that you had this uh, derivation of, I mean this the definitions of this uh, continuum hypothesis and then Newtonian to non-Newtonian effects and how they are coming into picture. So continuum hypothesis, we have discussed transport mechanism, we have discussed all the three transport mechanisms. The molecular transport mechanisms, types of that we have also discussed. Analogies, you have seen partial, total, and substantial time derivatives, how they are differing with each other. We have seen, we have derived the continuity equation, del rho by del t equals to minus of grad dot rho b vector. And in the substantial derivative, you should take rho by dt equals to minus rho del dot phi. And similarly, the momentum equation have been derived. I will be dictating again once del by del t of rho v vector equals to minus of del dot rho vv minus del p minus del p dot tau plus rho v. So this is in the vector form, and the below is the Cauchy's. So now the equation of change for the non-isothermal system comes into picture. Right? So next, around 22 slides, 23 slides rather. If I will be showing you how many slides, very important slides are there. So see, this is this to remove it. So now 24 is there. Then this one last leave. This one you leave. Okay, so 22. So 22 slides are very important. So only 22 slides we have to focus, and it will take around 20 minutes for us to actually feel it. Okay, so let's expand it again. So why I am revisiting this slide? Because I myself found it a bit tricky or tedious while going through this, and that's why I am revising it for you. So energy equation, which is conservation of energy you are doing. So consider a stationary volume element fixed in the space through which the fluid is flowing. Kinetic energy and the internal energy may be entering and leaving. So all other slides, we have revised two lectures for a second, and we have revisited all the things that we have seen as a summary in this particular first hour of this particular lecture, and also we have touched on some of the main concepts. All the lectures and the slides that I have explained, they are having clear, clean solutions, thorough solutions, so you can revisit them, add up it to your study module. It will be very helpful. So I am just now re-explaining the entire non-isothermal system itself because it is very important, and then we will close this session. So there is no point of revisiting those slides and questions again because they are self-explanatory. So why not we should explain this particular slide. So considering a control volume element fixed in the space through which the fluid is flowing. So just imagine that control volume. Kinetic energy and the internal energy may be entering and leaving the system by convective transport. So kinetic and internal is coming because of the convective transport, because of the motion. Energy may enter and leave the system by heat conduction. So heat of the conduction is taking the energy out. Kinetic energy, the internal energy is taking the fluid in and out, heat in and out, energy in and out because of the convective effects. And there may be work done on the moving fluid by stresses, which is also a molecular process. And this include work done by the pressure and the viscous forces. So, so far this pressure and the viscous forces came, heat conduction came, and kinetic energy internal energy. Work may also be done on the system by virtue of external forces, for example, gravity. Okay. So this is very important equation, which is the conservation of energy equation. And the entire lecture will be moving around this particular equation. Here, the first term says rate of increase of the kinetic and the internal energy of that control volume. The control volume that we have defined, the volume element in the space through which the fluid is flowing. In that, the rate of increase of the kinetic and the internal energy will be equal to net rate of kinetic and the internal energy which is added by the convective transport plus net rate of heat addition by the molecular transport, which is conduction. So conduction is the molecular transport plus rate of work done on the system by the molecular mechanisms, for example, stresses, right? Okay. And plus the rate of work done on the system by the external forces such as gravity. The last. So first two slides were more or less same. Just those are written in terms of balances. So everywhere you are saying the net rate of kinetic and internal energy addition or removed by the convective transport plus net rate of heat addition by the molecular transport. So convective transport, molecular mechanisms, and then external force. So the kinetic energy is the energy associated with observ, observable motion of the fluid given as 1 by 2 rho v square, which can be written in the vector form like this 1 by 2 rho v. Okay, so this is the expression for that. Internal energy is the kinetic energy of constituent molecules. Okay, at the molecular level. So for the internal energy, the origin is coming from the molecular. In the frame of moving with the velocity v plus the energy associated with. So the internal energy is the kinetic energy of the constituent molecule calculated in a frame of the with moving velocity, frame moving with velocity plus energy associated with vibration and the rotation and also the molecular interaction of all the molecules. Those things will be there. So potential energy do not appear in this equation as preferred to consider the work done on the system by the gravity. Viscous heating source term is not appearing separately as already included in the rate of work done on the system by the molecular mechanism, that is stresses. That was the last second notice. So the chemical, electrical and the nuclear source terms can be included in right hand side of the overall conservation of energy of a specific consideration problem. You can add this chemical, can electrical, and if chemical reaction is this endothermic exothermic, based on that whatever thermal energy is transported, that can be added here. Electrical energy, nuclear energy, those things are added in the right hand side of this particular equation. So this is this. Right. Now let's see. Let's define energy vector E, which includes first three terms in the right hand side of the symbol, which is this. The first three term is because of the convective transport, because of the heat, whatever kinetic energy, internal energy addition is happening for the convective transport, and then whatever heat is added because of the molecular transport, which is conduction, and whatever heat is added because of this molecular mechanism, and whatever work is done on the system by mechanism, which is stresses that include the viscous dissipation also added, and that is defined in this particular right hand side E vector, which include the first three terms on the right hand side, that all terms except work done due to external forces such as gravity etc. So this is gravity, reaction, electric, or the nuclear source. This is so if you see this, this is the kinetic, this is the potential. Okay, this is the coming because of the conduction, which is the molecular transport. Because of that heat addition, and then there is this molecular mechanism based one, which is pi. So now this pi over v vector is this one. So how this pi over v vector is this is the work done on the system by Markov, which is stresses, which is explained here is viscous heating source term is not very rather it is taken care by the stresses in terms of rate of the work done on the system by the Markov mechanism. Right, so this is that mechanisms, this conductor, transport, and then another one was this terminated transport. Okay, so these all are the terms written in such a way for each direction. Okay. We already know that the total molecular stress tensor pi can be split into the two parts, which is one is because of the Davitoric. This will be normal pressure, and another is Davitoric shear stress. So if you split this pi in terms of p plus tau, then you will get pi dot v equals to pv vector plus tau dot v. And if you put that and rearrange the things accordingly, you will be getting this one. So where u vector, v vector, and h are internal energy, volume, and the enthalpy of the system per unit mass. So now this converting equation 1 in the mathematical form, how you are converting that equation 1, which was the balance of this is the equation 1 that you are going to convert in the mathematical form, this one. So if you see, this was the equation, and in this one pi dot v you are having p v dot tau dot v. If you just, we know that this one how this is just okay. So you just multiply this rho v, this is just rearranged in this way. And this, when you take common, this, so this we can pu plus pv we can enthalpy, and based on that enthalpy is coming into the picture. For this same E can be written in terms of enthalpy, right? So the rate of increase of the kinetic and the internal energy within the control volume element is this one, where U cap is the internal energy per unit mass, specific internal energy, and U rho U cap is the internal energy per unit volume. See,
Just density is multiplied, mass got cancelled, and then volume became
came into the denominator. Also, this kinetic energy can be defined in this way for all the direction x, y, and z. So, amount of energy entering and leaving across the face of delta x delta by delta g are written in this way. So rate of the work done on the fluid by the external gravitational force is dot product of the V and this one. Okay, so it will give you these things. So now substituting all the equations in the equation 1 and setting it out, finally we will get the final equation, which is coming up like this. Bigger equation, which is having the rate of increase of the energy per unit volume, is given, which is kinetic potential, is given by this rate of addition of the energy per unit volume by convection, rate of addition of energy per unit volume by conduction, and rate of addition, the rate of work done on the fluid per unit volume by pressure forces, and rate of work done on the fluid per unit volume by the viscous stresses. So the rate of work done on the fluid per unit volume by the external forces. So So all the things, external forces may be anything, be it reaction, be it nuclear forces, or be it critical forces. That can be. Okay. So above equation can be written including the potential energy per unit mass 5 as follows. So where you will be using you will just the z to be raised in a vector magnitude. You can write it like this, and z is elevation in the gravitational field. Thus, g vector equals to minus of that. Right. So in that term, if you see the if gravitational field is estimated at the time, the last term you can write in this way, and vector identity, you know this one. You can follow BSL for this particular expression if you forgot it, and rearrange it, you can get the final energy equation like this. See here, this is it is now not any potential you can write. This is general. So special forms of energy equation exist sometimes. So we have equation of change for kinetic energy as follows: obtained by dot product of the vector velocity vector with the equation of motion. Followed lengthy arrangement. Uh, okay, and you can get this one. So this equation of the change for the internal energy you can write. Okay, in terms of U. In terms of U also this can be derived. In terms of enthalpy also, this equation of change for the enthalpy is an element of inner element of fluid moving with velocity v. Equation of change in terms of temperature also you have derived, because that is the one measurable one. So this can produce temperature rise in the system with large viscosity and velocity gradient, like lubrication, rapid extrusion of the high speed flights. So these all are this was the main slide. So these were the key finding. So this is the main equation that we have derived. The detailed one was the last one, the complete energy equation. These were under some assumptions. So you see, for a fluid constant pressure, this will be becoming zero. For a fluid with the constant density, uh, uh, this rho by del ln by del T equals to 0, and then for a stationary solid, V vector equals to 0. So those things you can consider, and then get to know that these are the correlations which are coming up into the picture, that can be used, and they are in terms of the measurable quantity, that is temperature. All these equations can be derived for the in terms of thermodynamic properties like internal energy, enthalpy. We have seen it. But it is good to derive them for in the measurable terms, measurable quantity, because that is the one which is known to us. We can use any other transducers, some transducers, measuring instruments to actually have a knowledge about them, and then use these equations to relate our experiments, right? So that's why it is crucial for that. So that is it for this particular lecture. You can revisit this particular lecture, derive all the equations on a copy one by one, then you will feel it. Though these all the steps are in detail, but maybe there somewhere if it is left out. Right? So let's come back to our slide. So last week it was the boundary layer. So the, in today's lecture we have revisited complete course structure, also tries to revise some of the questions that we have solved. had a general discussion about. We have revisited the energy balance equation and the steps followed for that in very step-by-step manner. So I hope this lecture helped you uh, and it supported you in many sense. Thank you. Thank you so much. Thank you. So closing the lecture.